our notes packets to the continuity graphs on that next page. And let's talk about continuity intervals. So it says find the intervals on which the function is continuous. So we have a quadratic that is for x values less than 1. We have a linear function for x values greater than or equal to 1. Domain and range of a quadratic and a linear function are all reals. However, in this case, as x approaches 1 from the left and x approaches 1 from the right, they do not equal each other. Therefore, this graph is not continuous at 1. So it'd be negative infinity to infinity for its domain. And again, the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. Because it says find the intervals on which it's continuous. So it's not ever continuous at 1. Like, because left-hand limit doesn't equal the right-hand limit, therefore it's not continuous. This is an example of jump discontinuity. Now, you could say it's right-hand continuous, but this wants to know in general for the entire function, not. Okay, number 2. 1 is x, or the value of the graph is 1 for all x's except 5, and at 5 it's at 3. So therefore, again, this graph is continuous from negative infinity to 5 and 5 to infinity. At x equals 5, you have jump discontinuity. And then the reason the graph is not continuous is because the limit as x approaches 5 of f of x equals 1, which does not equal f of 5, which is equal to 3. So the limit exists, however, the limit does not equal the function value, therefore not continuous. Okay, this time we're not given a graph. So in order to sketch it, you're going to plug in the function value. So I would plug in 2 times 2 minus 10. And I get negative 6. So that means at x equals 2, we have an open circle at negative 6. And the slope of the line is up 2 and over 1. So since we're going to the left, it'll be down 2 and right and left 1, down 2, left 1. And then from 2 to infinity, the graph is at 0. So again, it says find the intervals on which the graph is continuous. So the limit as x approaches 2 from the left is equal to negative 6. The limit as x approaches 2 from the right is equal to 0. Therefore, the left-hand limit does not equal the right-hand limit. Therefore, it is not continuous at x equals 2, and we have jump discontinuity. The intervals, yeah. So it would be negative infinity to 2 to infinity. All right, to graph, I would probably first start by factoring the top to see if I have a removable discontinuity. So we get x minus 2, x plus 1, which means that x plus 1 cancel, and that this graph really looks like x minus 2 with a hole at x equals negative 1. Okay, so it's a linear function. At negative 1, we have a hole. So the limit as x approaches negative 1 of f of x would be equal to negative 3. However, f of negative 1 is undefined. Therefore, not continuous at x equals negative 1. And we have a hole, which is removable. Discontinuity. And my continuous interval would be negative infinity to negative 1, negative 1 to infinity. Okay, so let's turn to our notes to 1.3, day 2. So that was just a nice little warm-up at looking at continuity and graphs. So what I want to do with you today is we're going to actually investigate something called the intermediate value theorem. The intermediate value theorem is an investigation of continuity. It's important to understand how graphs appear for the intermediate value theorem. So again, part of the reason why we start with continuity and sketch it. So continuous functions, much like limits, have these properties that can be applied to them. So if two functions are continuous at a point, then the following combinations of continuity are also true. Are we good? All right, so we previously talked about composite functions. Composite functions are when you compose two functions together. All composites of continuous functions are they themselves continuous. Composites are thus continuous at every point at which they are defined. And for example, if f of x is continuous at x equals c, and g of x is continuous at x equals f of c, then g of f is continuous at x equals c as well. In other words, the limit as x approaches c is g of f of c. In our textbook, this is referred to as Theorem 7. So in our textbook, the homework might state Theorem 7. So Theorem 7 says if f is continuous at x equals c and g is continuous at f of c, then the composite g of f is also continuous at c. Bless you. Okay. So let's apply this. So it has show that f of x is continuous given the following function. So what we need to do is create two functions from the given function. So we're going to define two functions, h and g, from f of x. And what we want is for f of x to equal g of h of x. So we're going to write our functions in a way that h is composed into g. So that means g needs to be my outer function. So the outermost function in this example is the absolute value. So we're going to say that g of x is equal to the absolute value of x. And we know that the absolute value of x is a continuous function for all real numbers. If g of x is the outer function and we've represented it by the absolute value, h of x becomes the inner function, x sine x squared plus 2. And really what you can do is, by our properties of continuity, think of this as x times sine x times 1 over x squared plus 2. X is linear and therefore continuous. Sine x is continuous on its domain. And 1 over x squared plus 2, well, the denominator can never equal 0, therefore continuous. So by the properties of continuous functions, h of x is continuous for all real numbers. And by Theorem 7, the composition of function theorems f of x equal to g of h of x is continuous. Yes. Because so the only reason a fractional function would never be continuous is if the denominator is equal to 0. But x squared plus 2 can never equal 0 because it's a x squared plus 2. So if you tried to set that equal to 0, you get x squared equals -2. But we can't take the square root of a negative and get a real number. So there's no value you can plug in for x squared that would make that denominator 0. That's why that part is continuous. If it was like x squared minus 2, now it's a whole different ballgame, because now you could make x squared equal +2, and you can make it equal to 0. The intermediate value theorem. This is one of 3 important theorems from chapters 1 and 2. The intermediate value theorem says that if a function is continuous on a closed interval, that you are guaranteed every value in the range from f of a to f of b. So what it says is that a function that is continuous on a closed interval is guaranteed every value from f of a to f of b. So in layman terms, if y naught is between f of a and f of b, then y naught equals f of c for some c in AB must exist. So this is kind of like my n is like f of c. Okay. So I'm going to is my screen? So what this says is that if you have f of a and f of b, I feel like my name is beautiful. Like this should say f of a, and that should say f. Not that it matters. But basically, what this says is that if this is a point and this is a point, and the graph is continuous, every y value must live between them. Every y value must live between them. So, let's just take a random example. Let's say x is 1. Let's say the height for f of 1 is equal to 7. So we have the point 1, 7. We are told the graph is continuous. So it might go down, it might go up, it might come back down, it might come back up. We have no idea. At point B, which we'll say x is equal to 6, let's say the height of f of 6 is 5. What we know is that there exists a y value from 5 to 7 guaranteed. So if I said, does f of x equal 6.2, your answer is. If I said, does f of x equal 5.000001, your answer is. If I said f of x equals 0, your answer is. You don't know. So it might, but it might not. Because you have no idea what the graph is doing. All you know is that from here to there, it hits at least once. All you know. That's what the intermediate value theorem says. Intermediate meaning in between values. So the in between values always exist. If this changed, and now my x equals 6 is at -2, does this hold true? Does this hold true? Does this hold true? Yes, because now every value exists from -2 to 7. So you really care about the range. Yes. I'm going to say we're not going to do that. So the answer would be yes. It still would hold true, but they're going to give you like something it's a function. Like most graphs that we talk about in here are functions. So the ones I really want to do so they would never give you a case that's not a function. Or if they do, they're looking for you Like it would be more like IDT does not apply than it would try to trick you into giving an answer. Yes. No. Okay. All right, so I didn't give you like all of those bullet points in detail, but I gave you like most of them in summary. It's helpful just to like read them, because again, that's what I'm saying, but like sometimes reading words is helpful. So go ahead, just take a minute and read them. I don't know how to zoom in. So again, big idea is that it cannot take on two values without taking on all values in between. It will pass the vertical line test, does not have to pass the horizontal. Horizontal is 1-to-1, not function. Vertical is function. You can pick any value in between and it will exist. However, it does not tell me about anything above or below my f of a and f of b. It only guarantees between. So example 2, is there a real number that exists and is exactly 1 less than its cube? So for this number to exist, it must satisfy the equation x equals x cubed minus 1.
Desiree Hank, Luke Kozlowski, Tessa Kovach, Emmanuel Dominga, Emma Stenger, Spencer Thomas.
Should we say to come to the office?
Brody Havelka. Please report to the guidance office.
How? All right, so what you want to do in this example is think about the function itself. So you have x equals x cubed minus 1. And what we could do is set that equal to 0. So that gives 0 equals x cubed minus x minus 1. And if you think about the graph of this function, we would want to think about, okay, when would any of these be true? Now, if you leave it here in the original form, you have x equals x cubed minus 1. Well, that factors as x minus 1, x squared plus x plus 1. So again, doesn't truly help me. What it leaves is this idea that we could set this equal to 0 and use our calculator. So you have two choices, y1 equals x, y2 equals x cubed minus 1, or y1 equals x cubed minus x minus 1. Here, in this example, you would want to use second trace and look for intersect of the two lines. In this example, we would want to find the zeros of the graph. So let's take out our graphing calculators and do that. don't know why it won't let me make this bigger. There we go. Do you want to use y1 and y2 and find their intersect, or do you want to do y1 and find the 0? Okay, so you have x cubed minus x minus 1. So we'll start with looking at the zeros. Zoom 6 gets you in standard form. So again, we have everything set equal to 0. So we're going to find the zeros of our graph. So you had second trace. You want to go to 0. You're going to go below the 0, above the 0. You hit enter above and below. For guess, it doesn't matter. And we see that the 0 occurs at 1.325. 1.325. Similarly, you could put x cubed minus 1 in. You can put x in and graph. And when we put both in, we're going to go to second trace and go to intersect. And just get the cursor near where they hit each other. And we see once again they intersect at 1.325. So it says, is there a number that exists to satisfy that equation? The answer is yes. X equals 1.32, and you can write 4, 7, or 5. But remember, in calc, you must always have 3 decimals. Technically, you're right, it would be approximating, but because they only want 3 decimals in calc, equals also fine. Both would be fine. Okay, then it says use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. So what we need to do is find f of 0 and find f of 1. Because the intermediate value theorem says that all values from f of a to f of b in the range exist. So you need to know what is f of a. So in this case, it's 0 cubed plus 2 times 0 minus 1, which is negative 1. I need to know what is f of b, which is 1 cubed plus 2 times 1 minus 1. So 1 cubed is 1, 1 minus 1 cancel, and you get 2. So what we know is that polynomials are continuous. That is a part of being a polynomial. So at 0, you're at negative 1. And at 1, you're at 2. So we know that all values in that range must exist. Because we know that from A to B, we have a line. So that means everything exists. So it says use IVT to show that. So we have to show f of 0 and f of 1. So we would say that by IVT, f of x equals 0 because f of 0 equals negative 1 and f of 1 equals 2. Therefore, f of c will equal 0 between them. Okay. The function f of x is continuous on the interval -3, 9, with f of -3 equaling 0 and f of 9 equaling -12. Which of the following would be a correct statement concerning the existence of c? So again, we have 0 to -12. So in my mind, I'm saying, okay, the range is 0 to -12, guaranteed. Doesn't mean that it might not be outside of it, but what it does mean is that from -3 to 9, we are guaranteed within. So A says f of 12 equals 0. Well, 12 is outside my domain, therefore I know nothing about it. F of -1 equals -13. -13 is outside my range, therefore I know nothing. -2 is equal to -10. -2 is inside my domain, and -10 is inside my range. All right. And just to make sure, f of 8 equals 1. Well, that's in my domain, but that is not in my range, so it's not guaranteed. So therefore, we know that f of -2 could equal -10. So all it says is which of the following could or would be a correct statement given IVT. Yes. You have your paper, you could hand them it. All right, example 5. Find the values of a and b that make k of x continuous everywhere. Be sure to use the definition of continuity. All right, so we're back to continuity from the beginning of class. Definition of continuity says that the value must equal the limit. So I'm finding k of 2 for both functions and k of 3 for both functions. That's how I'm starting. So k of 2 plugged in here gives 2 squared minus 4 over 2 minus 2. And I get 0 over 0. So I can't find k of 2 outright. So I'm going to look at the limit as x approaches 2. Knowing I can factor my top and bottom. So the limit is equal to 4, and that would be the limit from the left. The limit as x approaches 2 from the right would be the bottom equation. So that's a 2 squared plus b times 2 plus 3. So I get 4a plus 2b plus 3. And in order for the function to be continuous, the left-hand limit must equal the right-hand limit. So I know that 4 must equal 4a plus 2b plus 3. However, at this point, I have a's and b's and nothing cancels, so I'm at a pause. So what we're going to do is look at the limit as x approaches 3 from the left, which is a times 3 squared plus b times 3 plus 3. So we get 9a plus 3b plus 3. And we're going to look at the limit as x approaches 3 from the right. So you get 2 times 3 minus a plus b. So you get 6 minus a plus b. And again, I know that in order for this to be continuous, the left-hand limit must equal the right-hand limit, which means, and again, I'm running out of room because I wrote big, that 9a plus 3b plus 3 must equal 6 minus a plus b. So I'll subtract 3. Add my a, subtract my b. So I have 10a plus 2b equals 3. And over here in blue, I have 4a plus 2b equals 4 minus 3, which is 1. What does this remind you of? So you have a system of equations where you can use elimination. So we'll subtract the blue from the red. So we get 10 minus 4, which is 6. 2 minus 2, which cancel. 3 minus 1, which is 2. So a is equal to 2/6, which is 1/3. And once you know a, you can use it to plug in to any of our functions and solve for b. So you have 10a, where a is 1/3, plus 2b equals 3. So you have 10/3. So you get 2b equals 3 minus 10/3. So 3 over 3 minus 10/3 would be like 9 minus 10/3. So you get negative 1/3. So you get 2b equals negative 1/3. Divide both sides by 2. And we get b is equal to negative 1/6. So those are the values of a and b that would make this function continuous. Yeah, so that's exactly it. They have the same variables, so you can eliminate any two equations with the same variables. And again, algebraically, we haven't broken any laws of algebra because all we did was subtract one function from another. No, it's okay. So they're all, so technically, like, I know what you're saying. You're saying, like, because one was from, like, the left-hand limit for 2 and the right-hand limit for 2, and the other one was from left-hand limit for 3 and the right-hand limit for 3. But at the end of the day, both came from the same k of x. So if one was like from k of x and one was from an f of x, then you're 100% right. We couldn't combine them. But because both the limits came from the k of x function that we were trying to create continuity for, and I needed that continuity, like I needed whatever the a was here to be the same a there, and I needed the b here to be the same b there. So by technicality, those functions were connected from the beginning. All right. So your homework is partially in the book and partially on a handout. So it's only a couple problems from the textbook. And then in your packet, it is the worksheet. So you're skipping the multiple choice IVT. I don't know what order I actually stapled them. It's the worksheet that says on continuity and IVT. It's 1 to 11. It's the worksheet. It says worksheet on continuity and IVT. It might be after the multiple choice. Yeah, it's the very end of the packet. So you have like 15 minutes in here to get started on that.